It's a little different from what you have. It sort of overlaps highly with the second half of the notes we passed out the other day. So let me just define the smooth principal series as being an induced representation from characters of A, basically, and which become characters of P, trivial on N. They're unitary on the imaginary axis. So we have an analytic family. In fact, we have two analytic families. We have two copies of C parameterizing these characters by the parity of the restriction to K. Gx by the right regular representation. At this moment, we only know two of these representations in individual. If I take delta equals 1/2, in other words, if I take, S equal to -1, in fact, that's what corresponds to -1/2 here, then I get just the functions on G mod P. If I take delta plus 1/2, then S equals 1, and that corresponds to the densities, the measures on G mod P. The normalization delta 1/2 is thrown in just to make the duality work out, so that ind chi -1 is the dual of ind chi, and I get that pairing. I pair the two functions by multiplying them and integrating. If I take two functions here with chi and chi -1, I take the product, then I get a delta factor there, and that's equal to 1/2, so I can integrate it. And that's the pairing between the two. If I take a unitary representation, then F bar will lie in the dual space. Then that means that chi -1 is equal to chi bar conjugate, and then F chi, and this is a positive definite integral. So ind is unitary, ind chi is unitary if chi is a unitary character. Any questions about this? Okay. So pretty much, so let me summarize what I did last time. Let me summarize this in a diagram. So we have a picture, two pictures in fact. So this is for m equals 0. The parity is even. This is for m equals 1. The parity is odd. In this case, all we know about at this point is that these things are unitary, and that if I have chi here, or chi -1 here, pairs with chi here, and these are dual. And over here I have more or less the same picture. This is unitary along here. Again, I have the same picture, chi -1 pairs with chi, but in this case we have a little bit of extra information. We have S equals 1 and S equals -1. These are duals, and this is sigma omega, and this is C infinity.
Emphasize what this picture means. I mean, what is the plane of the blackboard? These are characters of A.
These are the S's in the characters. So chi is equal to, I remind you, chi of X, where X is basically the A is diagonal matrices with real entries, and so it's determined by a character of the reals, and the character is absolute value of X to the S times the sign, plus or minus. So these two different sheets are parameterized by, in this case, chi of -1 equals -1, and over here chi of -1 equals 1. And so the restriction to K here is the sum of even characters and the restriction to K here is the sum of the odd characters. Okay. I think that answers the question. So just the parity of what happens to -1. The parity of M. M is either equal. I only need to choose M equals 0 or 1, because, okay.
This epsilon n notation, that was e to the I theta goes to e to the I n theta.
Huh?
The epsilon n notation.
Yeah, the epsilon n notation is it's a character. I recall they have the characters of K. K is a rotation group. I take the rotation corresponding to theta, go to e to the I theta. That's exactly right. Okay. And that's sort of summarized here. As I say, the best way to picture it. So all these representations, they look the same on K. So in some sense, all that varies in this picture is how G acts. The way K acts is absolutely fixed on each one of these sheets. And the restriction to K is pretty simple. It's just the sum, as I wrote down over there, of the epsilon n factors, n congruent to m modulo 2. And I'm looking mostly at, well, there are two different induced representations. One is the representation of G on the smooth functions, and the other is the representation of the Lie algebra and K on the K finite functions. And I write one, the end infinity is the smooth functions. If I leave out the infinity, that's the finite sums. That's a representation of the Lie algebra. Anyway, so the representation on the finite part is just a algebraic direct sum, and on the smooth stuff, it's a topological direct sum, which you get from Fourier series. Oops. I think, yep. Now, I can write down formulas explicitly for functions, so I can, so we have these functions phi n. Phi n is a basis, and the phi n's are eigenfunctions with respect to k. That is to say, they're taken into multiples of themselves by elements of k, and in particular, the eigenfunction character is epsilon n. And explicitly, if I have g equals a, b, c, d, then I can write p like this. This is the Iwasawa factorization of the element, and I get this, right? And so phi n of g is equal to this if I do all this. So this is an explicit formula, which is it's a calculation everybody should make once in their lives. We'll use that calculation in just a moment. Okay, and then I had explicit formulas which I worked out. I took my elements k and my raising and lowering things with respect to kappa. Excuse me, I have an element kappa, and I have my lowering and raising operators with respect to kappa, and those are those. And then I have explicit formulas which I work out like this. So we have, and this matches again with what we've seen all along throughout, where we write down formulas. Okay, and I do the calculation here, which I don't want to repeat. And I mentioned the sort of the basic fact of life is that every irreducible GK representation can be added into principal series. And Dragan has more or less proven that. This is the point in the lecture on last time where Dragan said he was going to prove it, and he more or less did prove it. So this is the past, not the future. Now I want to talk about intertwining operators. So intertwining operators are, it's a technical term for what happens when you map one principal series to another. So as I say, there are a number of reasons why you want to do that. First of all, what we're going to get, I hope, before the lecture is over, maybe, is sort of a real complete picture of what the principal series look like. And in order to do that, we have to answer a number of questions. So first of all, which principal series are isomorphic to which other principal series? There's a huge overlap, and we've already seen that implicitly. And some principal series are irreducible, and then some of them contain other things we already know about. So we really want to analyze the principal series completely, and it turns out the key tool in doing that is to understand the maps between the principal series. So in other words, what we want to understand is the maps Hom GK from I, as I did last time. I'm just abbreviating the in to I, and we're only looking at k finites. And again, you could put a infinity here. It's not very different in some sense, but and the g over here. But we'll sort of look at both simultaneously. It doesn't make life much more difficult. And the key tool in understanding the maps between principal series, or indeed the maps from anything into a principal series, is to understand Frobenius reciprocity, which says this. And as Dragan has explained, so it's a little redundant now, we want to understand Homs from V into n chi. What we look at is the quotients from Hom of A from V quotient NV into things. Or what we're looking for really is things in the dual space. In other words, what we're looking for are functions. So Hom GK from V into I chi are equal to Hom from the duals. I just look at the dual way it goes, and this is I chi minus 1. Excuse me, this is Hom A from V quotient n into chi delta 1/2. And if I take the dual of this, see, this is V mod NV, but the dual of V mod NV, see, V mod NV is the quotient of V by this, and the dual of that is the stuff annihilated by n. So, and I write this like this. And this is a hat here. Equals linear functionals. V goes to C, annihilated by, well, I have n here. This is n. This is new plus is what that should be. Okay. So I just want to get out things which, hello? Yeah.
There's some expression about this So can we say,
No, it's not, n squared is not 0.
pardon?
N squared is not 0. What do you?
Leo.
That plays no role whatsoever. You see, yeah, that plays no role. N squared is equal to 0 only in one representation of SL2, namely the adjoint, the Lie algebra itself.
Yeah, but this, when bracket,
No. So that's extremely important to understand. At least I think you're making a mistake. I could be wrong, but so in the Lie algebra, nu plus squared is 0. But that doesn't mean that it's equal to 0 on representations. Right? Even if, for example, if I have a finite dimensional representation of degree 4, say, then nu plus goes like this. And these are all non-zero. We've seen several examples now where nu plus acts by something non-zero. In the Lie algebra, nu plus squared is 0, but that's a very, I mean, not in the Lie algebra, excuse me, not even in the Lie algebra. In the standard representation in 2 dimensions, nu plus squared is 0, but that holds only, that's almost unique for that. There are only 2 representations in which nu plus squared is 0, the trivial representation and the standard one. Okay? Is that,
yeah, I was wondering what happens beyond SL2R because this bracket seems mean vector annihilated by some power.
no, in general, you replace this by annihilated by all elements in the Lie algebra. So in other groups, annihilated by all nu, a member of n plus. Okay, that's the replacement for that. Okay. Okay, so in looking for maps between principal series, we're looking for linear functionals which are annihilated, which are invariant under, annihilated by the Lie algebra or invariant under the group n. Now, okay, so let's look at that. So there are basically 2 kinds of n, and let me say let me summarize this. There's one thing which I've sort of. So annihilated by nu plus, if and only if invariant, if the group is acting, which it isn't always acting. Invariant under n plus, well, n. Okay. Now, so we have in chi, we want eventually to describe all maps from int chi to C, well, even, again, we'll put an infinity in here, which are n invariant. And there are 2 kinds. And one is very simple. I just take a function and I map it. We already know one. In other words, these are examples. This doesn't exhaust the set, but it gives you some that always, in some sense, always exist. So the first is I just take a function, goes to f of 1. That's an n-invariant functional. Now this corresponds to a map onto a principal series. What's the map and what's the principal series? What's one obvious map between principal series? The identity, right. And this map corresponds to the identity. So that everything sort of fits into some consistent situation here. This, on the other hand, corresponds to something else, but there are a few problems with it. Anyway, let's look at the other one. So formally, we have an integral. Formally, we just take a function. I have something called omega 1, lambda 1. This is lambda 1. And this I call lambda w. Lambda 1 is just corresponds to the identity map, but let's look at what the other thing. So formally, we have an integral that looks like this. This is n invariant. And if I sort of see what happens, so I can apply this. Of course, n invariance because the integral is invariant. That's simple. And let's see what happens with respect to a, because that tells us what the map is. Well, if I apply lambda w to Ra of f, and you track all this down, then you get this. And that means that this corresponds formally to a map into the opposite principal series. It happens to be the dual here, which is also the, so lambda 1, I chi goes to I chi, and that's just the identity map. And lambda w, by Frobenius reciprocity, I chi goes to I of chi minus 1. So at least formally, every principal series has a map into its dual principal series. It happens, for SL2, there is an accident that the dual is also the Weyl transform. So the W is something that involutes the involution of the diagonal elements, and it just happens that's minus 1 here. That doesn't always work out.
Could you remind what the latest W is?
Huh?
Could you remind?
Yeah, W is 0110. That's on my second slide. Guess you've forgotten the second slide already. No, anyway. That's and the key element, the reason it's key is because it takes P into the opposite parabolic, and it just switches the diagonal elements. Okay, and so it gives rise to, at least formally, and I have to check what the convergence questions are. So, let's see, let's look at lambda W. Lambda W is given by this integral, and the elements of n are parametrized by elements of r, so I change my integral from n to r by doing it this way. Nx is that. And we have this factorization I wrote down a little while ago, and for this element, the factorization, and then I get to get the factorization of this, and so I write that out. I apply the Iwasawa factorization I did before, and this is what I get. And so what I get is that FWNX is equal to x squared plus 1 minus n plus 1 times f of kx, where k is whatever occurs in the factorization. Okay, and so lambda w explicitly on an element f is given by that. And now we want to know when this integral converges. Well, this is a bounded function. This k of x is f restricted to k is a smooth function. And so in particular, it's bounded. And so all we really have to worry about is this part. And this is equal to, well, if you look at the powers, it's asymptotically equal to 1 over x to the s, and x plus 1 rather, I'm sorry. And because the square cancels out with the 2 here cancels out, that's x plus 1. And so it converges for real part of s greater than 0. So let's add to my diagram here. So we have in this region, so we know a little bit more about the diagram. So lambda w converges the real part of s greater than 0. And the same over here. Greater than 0. Okay, so we're filling in more and more information. But in fact, we can calculate explicitly. So I have a formula which is, and I have some values of the f. I have these eigenfunctions for k, the phi n's. And so explicitly, I can write out my integral like this. And, well, let's see, I write this out. My epsilon, so my k of x, for x, my epsilon, my k of x is given by this. And so when I write this all out, I track this all down, I get this formula here. So this is the explicit evaluation of lambda w on phi n is given by this integral right there. And, well, for example, if I put phi 0, that's a function which is fixed by k. Then I just put n equals 0. I get this integral. And I evaluate that by the beta function formula I showed on Wednesday. Then I just get this. If I take phi 1, then for phi 1, what happens is the integral against x vanishes because this is even and this is odd, and the integral over r vanishes. So I'm just left with an I factor. N is 1, so I pull out an I, and then I use the beta function formula, and I get this. So I can evaluate my lambda w on 2 elements explicitly. If I evaluate it on minus 1, that's a conjugate. Phi of minus 1 is just a conjugate of phi of 1, so there's a minus I there instead of an I. Yeah?
So this intertwining operator, gamma or lambda w.
Lambda w is not the intertwining operator, it's the functional corresponding to Frobenius which arises from Frobenius reciprocity that gives rise to the intertwining operator.
Okay.
Okay.
But it maps from
chi to chi minus 1.
Yeah, to chi minus 1. If this is defined on real part greater than 0, why doesn't it also, can you extend it to real part less than 0?
Well, because yeah, but what happens to real part of s equal to 0?
But I understand that part won't be defined.
I mean, you get something, but it's not clear what you get. I mean, it's true, there'll be some inverse map, but again, in order to know that, you have to compute explicitly to see that it's not 0.
Okay.
Okay. I mean, you're right, you get something, you get some information, but the most important thing is that if you get these, the most important thing you see from here is that actually it's meromorphic everywhere, right? Because the gamma function is meromorphic everywhere. Okay. So what we deduce from this is that, so from the explicit, so at the moment it takes an explicit calculation and we see that so let me summarize. Because the logic is a little subtle, not terribly subtle. So 1, lambda w converges for real part of s greater than 0. And 2, lambda w when restricted to k-finite functions k-finite functions equals finite sums of the phi n's continues meromorphically. To all of C. Right. What's not immediately obvious, yeah, okay, well, we'll just see. There's something that's not immediately obvious, but we'll leave that. Okay. And you can see exactly where the poles are. For example, this has a pole at 0, and this does not. So lambda w has a pole on the m equals 0 sheet at s equals 0, and does not have a pole at s equals 0 on the m equals 1 sheet. Okay, and you can read off the poles. Here the poles are wherever s is even, and here the poles are where s is odd. Great. Okay. When
the gamma function equals 0, we're also going to have a pole.
let me ask you a question. Where does the gamma function have a 0? Let me ask that question again. Where does the gamma function have a 0? I didn't say it in my lecture. I forgot to. I should have. There used to be a joke. There used to be a very long, complicated joke about the zeros of the gamma function, but the point is there are none. So, whoops. What happened? Uh-oh. Oh, here we go. Okay. Huh? Oh, okay. I didn't mean to embarrass you that. Okay. So. Well, I didn't tell the whole joke. It's a long, long joke. It goes on for, and not only that, but it's an extremely nerdy joke, and even in the Princeton common room, it wasn't very funny. Tony Knapp was the one who used to laugh hardest at it. No. Well, I don't know, bad or good. I'm just describing the situation in the Princeton common room. Okay. Okay. Any questions so far, other than? Now, what's true is that you get some zeros of this thing. So this thing is sometimes 0 because the poles here will contribute to the zeros. And that's of importance, and we'll see later something about that, although I won't have time to go into great detail. Okay, and we can see also, so the lambda w's are meromorphic everywhere. So far I've only looked at 0 and 1. They generate the whole the whole principal series in some sense, generically, so to speak. And so, in fact, we see that it's meromorphic for all of the k-finite functions, which is not quite obvious, but it works out all right. And it's also, it turns out that it's actually meromorphic on the smooth functions, but there's nothing I've said so far that implies that. That's a rather more subtle fact. I'll probably talk about that next week. Okay. Okay, let's go back to, we had an open question about measures, which I raised before. And I want to answer that question right now because it's the same sort of integral involved. We had two ways of evaluating. So if I looked at omega, what I call omega infinity, the densities on G mod P, that's this in space. And we have two ways of evaluating linear function law. I don't know what function law stands for. Oh, yes, I do. Okay, linear functional. Linear function law is like Shangri-La. It's off in the Himalayas somewhere. Function land, yes. Okay, so that one way is just to evaluate over k, and then there was the other way was the integral we've seen now. So now we see what the point of integrating, of allowing ourselves to integrate either k over k or n, because somehow these occur in the intertwining operators. And so we have two different ways of evaluating this integral. And actually, if you follow through and evaluate the phi of 0 in different ways, then on one measure you get just 1, and on the other one you get this integral by the same sort of calculation we did here, and that's just pi. So the two measures we have, so we have two different ways of evaluating this integral on G mod P, and they differ by a factor of pi. It's one of the things that drops out. We could have done this calculation earlier, but then I just would have had to repeat the same decomposition. Okay, now the next thing I want to talk about, I want to explain the simplest relationship between, well, let me say, Dragan said there's some relationship between asymptotic behavior of matrix coefficients and embeddings in the principal series. And there's one basic formula which has something to do with that, although the calculation doesn't use any of the stuff that Dragan talked about. It's a calculation that goes, I think, back to Harishchandra. And we're going to need that later on for some purposes, and it's sort of easy to explain. So let me show. So there's one formula which relates asymptotic behavior of matrix coefficients to the Jacquet module, well, to functionals, linear functionals in a nice way. Let me explain that. Actually, let me give you the formula first. Holy cow, where is it? Uh-oh. Oh, it's not very, oh, here we go. Yep, okay. So let me explain first of all. So suppose I take a function at end infinity, and I take phi and its dual. And then the matrix coefficient of this pair is given by this function of g. I evaluate this, and it's given by this integral. Because that's my other, so I'm using the pairing. And I want to look at the asymptotic behavior of this as a function as g goes to infinity, or equivalently as well, g goes to the boundary of the disk at any rate. The boundary at g infinity, okay. And we want to just get some sort of Russ estimate. Now, this formula is rather simple, but it requires a restriction. I'm assuming only that r of the real part of s is greater than 0. So we're in the domain where the integral actually converges, the lambda omega integral. And now the theorem is that if I look at Ra of f phi, that it's asymptotic to delta to the 1/2 chi minus 1 of a. This is as a goes to 0. So this blows up times lambda w of f times phi of 1. So we have these two intertwining operators. See, chi is in the region where lambda w converges. Phi is in the opposite domain, but this certainly still exists. This is an n-invariant functional. This is an n-invariant functional. And this is the character. So what this says is there's a very weak relationship between asymptotic behavior of matrix coefficients and the n-invariant functionals on the two different spaces. And this is that. Okay, and this seems like a rather weak result in a sense, but of course I can look at the transform of f on left and right, and basically this gives the asymptotic behavior of f everywhere at infinity in all directions, not just in A. Okay. So this is Harishchandra's formula, which we want to prove. So this is very explicit. So remind you, Dragan has sort of a generic fact that there's a relation between asymptotic behavior and n-invariant functionals, and this gives you something very explicit. It's an explicit relationship between the two, but it's very weak. It's a very weak, and it has this restriction on chi, and it just says asymptotic without telling you the rest of the series, so to speak. Okay, so it's just an integral. We have to evaluate our integral, and again, here's where we're using the fact that this integral is given not by integration over k, but over n. So evaluating this integral, we do some fiddling around, we reduce it down to this integral, we make a change of variables here in n. We set this equal to the new variable, and then we fiddle this, and then we get that. And so my integral, this matrix coefficient, becomes equal to this. And now this is the a part of the asymptotic formula I want to demonstrate. So now I just have to look at this integral, and now I claim that this integral, as a goes to 0, the limit of this integral becomes the thing I had before, the phi of 1 times f of wn, which is the intertwining operator. Okay. Any questions? This is just formal so far. But I need the convergence of the integral. That's the reason for the restriction on S. So we want to see that this is this. And I write down the integral very explicitly. It's given by this rather messy expression, but rather simple to write down. Yep. But now we need a little analysis. Phi and f and phi are bounded on k. So the integral is bounded by some multiple of this. See, if I have my restriction r of es greater than 0, but that means that this whole thing, this part and this part together are less than this. And so there's a bounded convergence theorem somewhere from a real analysis that says, under those circumstances, I can take the limit inside the integral. And if I take the limit inside the integral, then this just becomes, a goes to 0, so this just becomes 1. And this goes to the lambda w, and the other part goes to phi of 1. And so that everything works out all right. Okay, we'll see later. We'll see later that we can actually write down a formula which is good everywhere in all principal series. But there's nothing we've said so far that, again, this technique is restricted very definitely to this case. What is what? K of x is the, yeah, it's the k part of something. Let me write it down. K of x was the k part of Wnx, which I had an explicit formula for. It's equal right. Okay. Okay, so that's the first, as far as I know, this is the first very explicit relationship that we have between these. As I say, there is a refined version, but we won't see that till next week. Okay, now, I next want to show how the finite dimensional, so as I say, we're basically trying to examine the principal series and sort of understand pretty much everything that we're looking at in these diagrams. And the next step is to see where we've claimed that every representation embeds into some principal series, and of course the finite dimensional ones are the simplest. I just erased something I didn't want to erase. Well, that's life. I'll draw this later. So let's look at the finite dimensional representations. Now I have to say I didn't get time to prepare this, so we have to do it all on the board. So let's look at a finite dimensional representation. So let's take, it has dimension n. Now we have a little diagram for this. We can look at the weights, look at the action of, this is something we've written down in various guises before. Let's look at alpha, nu plus, and nu minus. Remember, these form a trio. Alpha was this, nu plus is this, and nu minus is this. And this is for the group A. This is in the Lie algebra. This generates the Lie algebra of A. This generates the Lie algebra of N. This generates the Lie algebra of N bar. Now, all I need is a little diagram that works like this. We have, let's see, N weights. So there, it has dimension N. So these break up into eigenvalues of alpha. And the one of dimension N starts out like this. So, and we have a character of this. X goes to, well, x1 over x goes to x to the n. And then, no, excuse me. So the weights of this representation, the eigencharacters of this representation look like this. see, there's something I want to say. No, I guess not. I forgot what I was going to say. And nu minus goes like this, and nu plus, well, nu plus goes like this. And an arrow here means that something acts by something non-zero. Okay. Right, so this is a little diagram of the finite dimensional representation. Now, we want to embed this into principal series. And so this is my space V, so to speak. Here's a picture of V. What's this space? So if I wanted to embed into principal series, this is the space I have to calculate. What is this space in this case? Sarah? Okay, your name is Sarah for the moment, yes. Who's speaking? Oh, okay, yeah? Yeah, because anything else, so this diagram says that nu plus takes this weight and multiplies it, gives this weight times something non-zero, and then applied to this weight, it gives this weight times something non-zero. So everything else from here down is in the image of this. So this is equal to this, the whole space modulo the lower weights. And so as an A space, it's equal to x goes x minus n minus 1. Okay, so we've calculated our first quotient like this explicitly. I'm sorry? No, finish.
I saw the answer.
But probably somebody else didn't.
You couldn't figure out why it was the lowest weight and the highest weight.
Which is the low? I always get it confused. Which is lowest weight and which is highest weight?
Highest weight is cohomology. Variance is
So which is highest weight and which is lowest weight? And this diagram, which is, I don't know, I always get it confused. It's one or the other. Anyway, this is whatever you want to call it. This is this. It had highest and lowest. You can, I don't know, you can look in a mirror if you're confused. But no. Okay. And so we know this, and let's see. So now, and delta 1/2 is x goes to absolute value of x. And so if V is finite dimensional, so here's another fact we now know. If V is finite dimensional of dimension n, then it embeds into a principal series with chi times delta 1/2 equal to x goes to x minus n minus 1. So in particular, so in particular, if I take, am I right? Something's wrong. If I take n equals 0, if I take n equals 0, oh no, it's dimension, I'm sorry, n is a dimension, that's right. So if n equals 1, the representation is trivial. And in that case, this is 0, and we get exactly what we had before. It embeds into the PS m equals 0 and s equals minus 1. That's right. Okay. And so we have, we can add to our diagram. And the parity changes. If n is even, then you see the parity of this character is minus 1 goes to minus 1 to the n minus 1. And so as n varies from even to odd, you get different sheets. So we can add to our diagram, which I didn't want to erase. I didn't mean to erase, rather. Hello? I'm sorry.
Could you explain again how you get the parity M?
Yeah, the parity of m is the restriction to plus or minus 1.
Yes. But which M do you choose for?
Yeah, see here, so plus or minus 1 lies in both the compact group and A. And so I can detect from what it does to A, I can detect from these weights what it does to minus 1 because it lies in A. And minus 1 goes to minus 1 to the n minus 1. So if n is odd, then the parity is even. And if n is even, then the parity is odd. So we get, I'm not going to draw both sheets. I'm just going to draw one sheet. A very gross pun just occurred to me, but we'll put this in. So here's s equals 1, s equals 3. S equals 5. Here's a real part of s equals 0. Here's s equals minus 1, minus 3, minus 5. This has the one-dimensional representation, which I'll call FD1. Probably it's bad, but anyway, this signifies the dimension. This is FD3, this is FD5, and so on. Okay, so we've added to our knowledge of what the principal series look like. So these are where all the finite dimensionals embed on the sheet for parity, m equals 0. And now, let's see, so we know what happens here. We have these things embedding into this side. And on the other hand, so what we have is over here, we have FDN included in principal series of x to the, I think, minus n. I can't, well, anyway, whatever it is, I don't do this. And then there's some quotient. And over here, we have the opposite. We have PS minus star goes to the dual of FDN, goes to 0, and there's something which occurs here. So we have an exact, short exact sequence on each side. And this works like this. So we not only, so by looking at the left-hand side, we see where the finite dimensionals are, but that tells us something about what happens on the right-hand side by duality, where the finite dimensionals occur as quotients. And for SL2, the finite dimensionals are their own duals. And so this can be identified with FDN again. Okay, so we've learned a little bit more about the way things decompose. Any questions? Oh, okay. Okay. I don't know. So let's look at the unitarity question. We know that these representations, so let's see, let's draw in all the unitary things. We know that these are unitary because of we have this positive definite inner product. We know that this one is unitary, just because it's a trivial representation. It's easy to see that the rest of these can't be unitary. Unitary representations have to be bounded in some sense, and these are not bounded. But we can learn a little bit more from the intertwining operators. So we have the following fact. If V is unitary, then that means that V dual is isomorphic to V conjugate. So that means I have a pairing between V and its dual conjugate. And so this means that I have this. And, well, let's see. I chi conjugate is equal to I chi bar. And if I chi, let's see. Let me just summarize what happens. So I chi, and so in this condition, so if it's formally, so it's formally unitary. Well, I have at least a pairing which is, so it's called Hermitian if I have a pairing between. So V is called Hermitian. If there exists a G invariant pairing F dotted with F bar. So looks like this, and it's unitary if this is positive definite. Okay, and a little formal calculation will show that I chi is Hermitian if and only if chi is equal to chi bar, and those are the unitary ones we've seen, or chi is real. So the possibilities for unitary representation can be marked out on the diagram by a cross. So we have here, these are where we know are unitary. Again, I'll draw both sheets. Here's where we know are unitary. And so the question about unitary representations is, which of the real principal series are unitary? And that's an interesting question. It turns out the answer is as follows. If I look at the m equals 0 sheet, then the unitary representations among the principal series themselves are these, which are isomorphic because I have these intertwining operators taking this to this. And over here, there turned out to be none. There are no extra principal series other than the ones coming from the unitary principal series axis. The reason for that can be deduced from stuff we have, although it's partly a little bit subtle. So I have a map from this. I explained all this. We have this map TW. So we do have a pairing which makes something Hermitian between this and this. So in order that n chi be unitary but chi not be unitary, it's necessary that chi be real. If chi is real, it's n chi will be unitary if and only if the pairing. So we have a map from one of the real things to its opposite that gives a Hermitian pairing of some kind. The question is that Hermitian pairing positive definite? And now for m equals 0, on the m equals 0 sheet, we have a pole of the intertwining operator TW. That's the intertwining operator coming from lambda W. That has a pole. And if you think about it, what that means is that the pairing is positive there. You can sort of fiddle a bit and see the pairing is there. And then that gives you a positive definite pairing. It shows that the pairing you get is unitary, at least in a neighborhood here. And that means that the signature of some form on the K finites is positive. But it can't change. That signature can't change until you reach a place where you get a 0. And the first 0 that occurs for TW occurs at s equals 1. So what you deduce from that pole with a little fiddling is that all these are positive definite. Now over here, the TW doesn't have a pole, and in fact, TW is equal to 1 on phi of 1, and it's equal, I on phi of 1, and it's minus I on the other one. And that means that the signature of that quadratic, that Hermitian form is plus or minus 1. So that's not positive definite. That means that this can't be positive definite in here. So that means that there are no, even though I have a Hermitian pairing, that Hermitian pairing is not unitary. And there's some other thing which says, which is a little bit tricky, but basically there's the relationship between matrix coefficients and asymptotics. Intertwining operator says that I can't go beyond this point. I can't have a unitary representation outside of this strip. So the only possibilities are here, and it's not unitary in here, and so this doesn't work out like this. So these are not unitary, but these are. And so among the principal series, the only unitary representations is marked by this cross. Okay. Okay, it's kind of a fiddle. We'll give some more details of how this works out a little bit later. We're going to normalize the intertwine. The hard part, so the second part, for m equals 1, everything I've said is actually rigorous. I haven't explained, there's some tricky part I have to explain about how these are positive definite, but I have to normalize my intertwining operator, which I haven't done yet. Okay. So, are there any questions aside from whether I know how to spell or not?
Actually, I'll go through a lot of this more slowly.
Yeah, thank you. Thank you. Okay. Right, you're going to see this several times. This is called the complementary series. I think Peter's going to do this. I hope I'm not advertising falsely. I think he's going to explicitly calculate what you're not going to do that? No, okay. At 11 o'clock last night, he was wildly enthusiastic about doing this. So he must have slept on the question. Okay. That's what Bargmann did. So the original paper by Bargmann, where he analyzes these representations, Bargmann actually calculates explicitly what the Hermitian pairing is and shows it's positive definite. Okay, I'm going to stop here. The next theme is the Bruja filtration. We'll see. So there are a number of things to be taken up. One is this question of extending the intertwining operator to all of the C infinity principal series instead of just the K finites. And a finer, then also what I want is a finer description of asymptotic behavior, other than the one we have, the weak one we have. So we just go very fast through. And then I have to talk about characters. And I'm sure you have lots of questions about the last part of the talk. Okay, thank you.